Thermochemistry Part 2. Topics for today: calorimetry, specific heat, symbol S, and Hess's law of heat summation. How is heat measured in a chemical or a physical reaction? Now, the process for doing this is called calorimetry. Calorimetry originally was for measuring calories, which is a unit of heat. It's not a unit of chocolate cake or apple pie. Here are some terms that we have to know. The first term is specific heat, symbol S. Heat needed to raise the temperature of 1 gram of a substance by 1 degree Celsius. Here are some examples of specific heats. So if we take a look at water, you can have water liquid and water solid. You notice that two different specific heats. This means if you have equal masses of both of these, water and ice, and you applied the same amount of heat to both, the ice would show twice the temperature change as the water. So the water is able to hold a lot of heat without having its temperature change very much. We can also check out these two metals, aluminum and iron. Again, if you had equal masses of both, and you applied the same amount of heat to both, the iron would show twice the temperature change as the aluminum. And we'll be doing some problems, I think, where they're going to be asking you about that. Next value we have is heat capacity, which is the heat needed to raise the temperature of a given quantity of a substance by 1 degree Celsius. Here are some formulas you want to jot down. First one, we're going to be applying with the specific heat questions. Q, which is the heat, is equal to the mass times the specific heat times the change in temperature. Specific heat, or not specific heat, I'm sorry, but heat capacity is equal to the mass times the specific heat. Now, heat is also then equal to heat capacity times delta T. You might see a problem or two where they talk about the heat capacity of the calorimeter, so we'll be using that formula there then. Lastly, we have delta T. Now, you have to make sure that delta T is always a positive number. So even though it says T final minus T initial, sometimes you want to find the absolute value of that. So delta T has to be positive. Now here's a bomb calorimeter. Bomb calorimeter has a constant volume in it. And constant volume is, remember, what we had when we talked about delta E, which is really change in internal energy. Now, I know I used a U before, but that's because the author of the text you're using had a U. But a U or an E means the same thing. So in our bomb calorimeter, we have a constant mass of water in here. So the mass of the water doesn't change. We have our bomb in here where we'll do our chemical reaction. And let's say heat will be released, absorbed by the water. We have a stirrer to make sure that the heat gets evenly spread throughout the water. So we'll have a constant temperature of the water. And so they actually use these things for, like, you could burn, for instance, a little piece of chocolate cake to see how much heat is produced when that chocolate cake is completely burned, rather than trying to figure out all the different substances in it and their masses and then look up values and do a lot of math with it. Now, we're going to be using in the lab just styrofoam cups. And when we calculate the heat effect now, it's going to be delta H, because here it's done under constant pressure. And here the pressure is the pressure of the air. So pretty much the same idea. We have insulated system, isolated like that from the environment. We have amount of water that can change. That's important because you have to know how much water is going to be in it. We have a stirrer to make sure the water gets moved around so the heat will be spread evenly throughout it. And we have a thermometer to measure the temperature. How much heat in kilojoules is given off when an 869 gram iron bar cools from 94 degrees centigrade to 5 degrees centigrade? The specific heat of iron is 0.45 joules per gram per degree. Change in temperature is 89 degrees. I notice that I made sure it's a positive number. Here's my formula. I'm going to plug in my values now. I cancel my units, get my value, and because I want in kilojoules, I'm going to divide my answer in joules by 1,000. Here's a little bit more involved question, but it's one you're going to run into in the lab, I'm sure. So let's say we have a styrofoam cup, and it's going to serve as our calorimeter. We have 100 grams of water in there. Now the water temperature is 22 degrees. Now I'm going to take a 27-gram piece of a metal and drop it into the water. That metal is going to be heated to 100 degrees before I drop it in. So what's going to happen is the metal is going to heat up the water. So the temperature of the water is going to increase while the temperature of the metal is going to decrease. Eventually, they'll become at the same temperature. Here comes the metal now. And the temperature goes up to 22 degrees. So the water temperature went from 22 to 26 degrees, a 4-degree rise, while the temperature of the metal went down from 100 degrees all the way to 26 degrees. Now we're going to need that in the last step of the calculations. So the metal underwent a big temperature change while the water underwent a small temperature change. So how many joules did the water absorb? So to figure that out, we have to know the mass of the water, the temperature change of the water, and the specific heat of the water. Here's our formula. Now I plug in the mass of the water, 100 grams. Temperature change is 4 degrees, and that's the specific heat of water. Cancel out my units, and I get an answer of 1673.6 joules. How many joules did the metal lose to the water? The same thing, because heat lost by the metal equals heat gained by the water. And then lastly, what's the specific heat of the metal? Now, I would take my equation, here's my equation up here, and I would solve it for a specific heat, which is S. So it's going to be Q divided by M times delta T. Here's my formula then. I plug in my values. Now I want you to note 74 degrees was my change in temperature of the metal. It went from 100 degrees down to 26 degrees. It's very common for a student to plug in the same temperature change that the water underwent for the temperature change of the metal and thus get the wrong answer. Now I solve it mathematically. Here's my answer. Notice that none of the units change. Now here's a question very similar. It's a long question, but we just want to copy out the data. So we have the mass of a solid heated to 100 degrees centigrade in boiling water. Carefully add it to the coffee cup calorimeter that has 50 grams of water in it. The water temperature goes up from 25.1 C to 28.49 C. What's the specific heat capacity of the solid? And this is the same kind of question as I just solved for you. So I want you to stop the video at this point and see if you can solve this. And then come on back and check the solution. All right, here's the solution. Our plan will be to find the heat absorbed by the water in the calorimeter and find the heat released by the sample, which is going to be the same, and then find the specific heat of the sample. I'm going to go to another slide to start this. All right, to find the heat absorbed by the water in the calorimeter, I have my formula. Heat equals mass times temperature change times specific heat. I plug in my data. Notice the mass of the water now. Everything is water. Mass of water, temperature change of water, specific heat of water. Now here I'm doing it in calories per gram per degree. I get 169.5 calories. Now remember, that's also the heat that was lost by the metal. So to find the specific heat of the sample, I'm going to take the heat lost by the metal and divide it by the mass of the metal times the temperature change of the metal. So here are my values. One thing I want to mention to you, make sure when you're down here that on a calculator you say divided by not only this mass here, but divided by the difference. If you say the mass times the difference, the calculator will think the difference is on top here, and you'll be off by quite a bit. And there's my final answer. Now if I wanted my specific heat in joules per gram per degree, I just multiply this answer by the conversion factor from calories to joules. Now here's a different type of question. I just want to go through the solution to this one because you might see one like this in a textbook. A 30.14 gram ball bearing, here's the specific heat. is at 117.82 degrees centigrade. Dropped into a styrofoam cup containing 129 grams of water at 20 degrees. What's the final temperature of the water in the cup? Okay, so let's see what we know. We know that the heat lost by the ball bearing equals the heat gained by the water. So Q1, which is the heat lost by the ball bearing, will equal Q2. Now Q1 is equal to the mass of the ball bearing times the specific heat of the ball bearing times the temperature change in the ball bearing. Whereas the heat gained by the water is equal to the mass of the water times the specific heat of the water times the temperature change of the water. If I make all my substitutions in, looks like a pretty big equation. This is the mass of the ball bearing. This is the specific heat. Now I want you to note that I have final temperature here, and it's the initial temperature minus the final. That's because the final temperature of the ball bearing will be less than the initial temperature. And I want my temperature change to be a positive number. Whereas down here, I have final temperature greater than the initial temperature because the temperature of the water is going to increase. Now solving it mathematically, simplifying the equation, I come up with this. I left out some of the units on purpose just because it would kind of complicate things. So now I want to simplify a little bit more, so I'm going to add 10,795 to both sides, and I'm also going to add 14.3 TF to both sides, and I wind up getting that. Then dividing by 554.3, I get my final temperature to be 22.5 degrees. And that all fits. You notice that the water temperature went up just a few degrees, while the temperature of the ball bearing really dropped a lot. All right, the last section we're going to look at is called Hess's law of heat summation. If two or more chemical equations can be added together to yield the desired equation, then the delta H values can be added as well. Now here's my example. If we have an equation, A plus B yields C plus D, delta H, let's say 1 for that. Now we have a second equation. Notice that C and D are the products of the first equation, while C and D are the reactants of the second equation. Now, I can cancel things out that are both produced and then used up. So I can cancel out C and D from both sides. And then if I bring down what's left, I have a new equation with delta H value, I'm going to call it delta H3. So therefore, delta H1 plus delta H2 equals delta H3. Now here are the two rules for using Hess's law. If you have to reverse an equation, then a sign of delta H will switch. So if it was positive, it'll then become negative. Also, if the coefficients in the chemical equation are multiplied or divided, then you have to do the same to the delta H value. Let's take a look at a couple of examples. So here we go here. We're asked to find delta H for this particular equation up here by using these two equations. So we have to manipulate them somehow and add them together so they'll add up to this. So how do we know how to manipulate them? Well, let me show you. First of all, we want to have H2 gas and half O2 gas on the left of the arrow when we're done. And it's in the first equation, it's already on the left. So I'm going to keep this equation just as it is. I'm going to just copy that one. What about the second equation? Well, if you notice, H2O liquid is on the right. Here I have it on the left. So I'm going to take this equation and reverse it. Here I go. Now, look what happens when I add them up. Notice I can have H2O gas on the left and H2O gas on the right. So I can simplify this by canceling both of those out. Now I can't cancel anything else out. I can't cancel out H2 with the H2 and H2O because these are two different substances now. If I bring down what's left, I get this. And then I compare this to what I wanted to find delta H for. And you notice the equations are exactly the same. So if that's true, then I could add my delta H's and I'm done. So this is how I can get a delta H for an equation that I couldn't find anywhere, that I would have to do an experiment for. By looking up a couple of data equations, I can manipulate them. Let's try another one. Now I want to find delta H for this equation up here by using these two. So I'm going to follow that same process. First of all, you notice that I have CO2 on the right, and this is the only equation with CO2 in it. You notice that there are two of them, and there's only one in this equation. So I'm going to have to multiply this entire equation, including that value, by 2. So what about this one? Okay, here's my CO, and it's on the right. But in my data equation, well, my equation I want to come up with is on the left. There are two of them. Here there's only one. So I'm going to have to take this equation, multiply it by 2, and reverse it. Okay, so I'm going to add them together, and let's see what I get. Okay, what can I cancel out? Well, I can simplify the O2. There's one O2 here, but there's two O2 here. So I can cancel out one O2 and just one of these. So there's an O2 still left up there. I can cancel out the 2C solid for both sides. That's gone. But there's nothing else I can cancel. So if I bring down what's left, you notice that this equation looks just like the one I'm trying to find delta H for. Therefore, I can add these delta H's together. And there's my answer.